Welcome to another edition of The Explainer. Today, we're digging into one of the absolute most critical, yet honestly frequently misunderstood foundations of our entire global energy landscape. I mean, for decades, we've kind of just taken the steady hum of baseload power for granted, right? But right now, there is a massive shift happening right beneath our feet. It's a shift that's reshaping national security, technological leadership, and literally the grid that powers our daily lives. We are talking about the global uranium supply shock. Okay, let's just jump right into the numbers. $106. In January of 2024, the spot price for a single pound of uranium hit this staggering figure. We're talking a massive 17-year high. And to really grasp how wild this is, we have to look back a bit to 2011. After the Fukushima accident, global uranium demand just plummeted. Reactors closed, projects were shelved, and the price of uranium completely tanked. That led to a decade-long slump in mining and exploration. But then, well, suddenly that surplus evaporated. The market woke up and prices absolutely skyrocketed. So, that brings us to the biggest question of the day. Why is the world suddenly scrambling for uranium? I mean, what exactly happened between that post-Fukushima slump and today to trigger such a massive, urgent resurgence in demand for this radioactive element? Well, the answer isn't just buried in the past. It's actually deeply tied to the highly advanced technologies we are currently building for the future. Let's get into Section 1, the new uranium boom. The real driving forces behind this new boom might actually surprise you, because we aren't just talking about your traditional massive nuclear power plants anymore. Sure, the world is desperate for diverse baseload power to back up renewables, but there is this massive, focused push for small modular reactors, or SMRs. These are advanced next-gen technologies meant to power remote areas, heavy industry, and here's the real kicker, artificial intelligence data centers. The sheer computing power required for AI is demanding unprecedented amounts of electricity, and tech giants are positioning SMRs as the ultimate solution. The stakes here are so incredibly high that in 2024, the U.S. Department of Energy received $2.7 billion in congressional funding. And to be clear, this wasn't just pocket change. This was a highly targeted, urgent investment aimed squarely at revitalizing the domestic uranium production industry. The government basically issued orders to rebuild the nuclear fuel supply chain from the ground up to fix a glaring systemic reliance on foreign suppliers. Moving on to Section 2, powering the modern world. Before we go further, let's make sure we're on the same page about the material itself. Uranium is a naturally occurring, weakly radioactive element. It's scattered all over the Earth's crust, mostly in unique geologic deposits like ancient sandstones. When it gets mined and processed, which involves a whole lot of crushing, grinding, and chemical leaching, it is turned into a concentrate called triuranium oxide, or U3O8. In the industry, everyone just calls this yellow cake. This specific powder is the absolute baseline essential ingredient required for nuclear reactor fuel. If you picture a bright yellow powder packed away at a processing plant in Texas, it looks deceptively simple, right? It just looks like colored dirt. But this exact substance eventually provides about 20% of all domestic electricity in the US and roughly 10% globally. It heats major cities, it powers massive maritime vessels, it even helps produce critical medical radioisotopes. But here's the catch. You absolutely cannot just shovel this yellow powder straight into a reactor. Which brings us to Section 3, the nuclear fuel cycle. Now, this is where the supply shock really starts to make sense. The nuclear fuel cycle is just incredibly long and complex. Stage 1, literally just exploring for a deposit and getting a mine developed, can take an astounding 15 to 30 years. Then, once you finally have the mined material, converting, enriching, and fabricating it into actual usable fuel takes another 2 to 3 years. And finally, using it in a reactor and managing the spent fuel takes another 7 to 15 plus years. This is absolutely not a supply chain you can just switch on overnight. And one of the biggest technological headaches in that middle 2 to 3 year phase is enrichment. See, natural yellow cake only contains about 0.72% of the fissile isotope uranium-235. To actually sustain a nuclear chain reaction in most commercial reactors, you have to enrich that concentration up to between 3 and 5%. Doing that requires complex chemical reactions to turn the powder into a gas and then spinning that gas at insane speeds in advanced centrifuges. It is a massive, highly technical bottleneck in the global cycle. But you know what's really fascinating? It's how the business side of this actually works. You might assume uranium is traded on an open, centralized exchange, like gold or oil or copper. Well, it isn't. The market is incredibly opaque. Roughly 85% of all uranium is secured through long-term direct contracts between the buyers, which are mostly utility companies, and the miners. These contracts lock up supply for anywhere from 2 to 10 years. So you have a secretive, super rigid market that simply can't adapt quickly to sudden spikes in demand. Let's look at Section 4, the Great Supply Divide. The disparity here is just staggering. The United States is literally the world's largest consumer of uranium. As we mentioned, nuclear power provides a full 1/5 of domestic U.S. electricity. Yet, despite this massive appetite, the United States currently produces less than 1% of its own commercial uranium requirements. In fact, in 2024, U.S. production contributed less than 0.5% to the total global output. The gap between what the U.S. needs to keep the lights on and what it actually pulls out of its own ground is massive. So, if the U.S. isn't mining it, who is? Well, in 2023, global production was dominated by just a handful of countries. Kazakhstan led the pack by a huge margin, accounting for roughly 39% of the world's primary uranium production. To put that into perspective, Kazakhstan nearly exceeded the combined output of the next 3 largest producers combined: Canada, Namibia, and Australia. Ultimately, just 6 countries accounted for over 90% of the entire world's estimated uranium production. But remember, mining is only the very first step. You still have to enrich it, right? And the enrichment choke point is even tighter. More than 99% of the world's uranium enrichment capacity is tightly controlled by just 4 foreign entities: Rosatom in Russia, the Urenco Consortium across the UK, Germany, and the Netherlands, Orano in France, and CNCNC in China. In the US, there is only one facility producing low-enriched uranium for commercial use, and honestly, it's actually controlled by a European-owned corporation.
Section 5. Choke points and risks.
When you rely on a 30-year supply chain that is spread out across foreign nations and totally opaque markets, the risks compound rapidly. We are dealing with geopolitical instability and rising international tensions. We have single points of failure where maybe only one domestic facility exists for a crucial step like milling or conversion. Add in transportation vulnerabilities, since we heavily rely on external shipping networks to move radioactive materials safely, and tightening regulations. All of this creates a deeply fragile environment for supply reliability. And here's where it gets really urgent. As we look to the future of those AI data centers and the new small modular reactors, the supply risk actually intensifies. See, these advanced reactors require a very specific type of fuel called HALEU. That stands for high-assay, low-enriched uranium. This requires enriching the uranium-235 isotope much higher, up to between 5 and 20%. The problem? Commercial-scale production of HALEU is currently limited almost exclusively to Russia and China. It's a severe product dependency risk for the next generation of American energy technology. But look, the situation is not without hope. The United States actually has significant untapped potential right under its own soil. Modern assessments from the USGS show massive undiscovered and unmined resources in sandstone deposits across the Texas coastal plain, the Wyoming basins, and the Colorado Plateau. By the end of 2024, the U.S. had an estimated 468 million pounds of economically recoverable, reasonably assured resources in the ground. So the material is definitely there. The real challenge is finding the time and building the infrastructure needed to actually get it out and process it. Which leaves us with one final, incredibly pressing question. The U.S. government clearly recognizes this massive vulnerability, hence the $2.7 billion injection to revitalize the domestic supply chain. But with a complex fuel cycle that literally takes decades to spin up from exploration to an operating reactor, will this investment actually be enough? Can the United States restart its dormant uranium engine and secure its own enrichment capabilities before the surging energy demands of AI and modern tech completely outpace the grid? It is a serious race against time, and the stakes couldn't possibly be higher. Thanks so much for joining me on this explainer, and we'll see you next time.